Hop back over here and give you a chance to warm up. And while you're doing your thing, we're gonna go like this. Mm-hmm. Awesome, you did it. And now let this guy. Okay, looking good, looking good. All right. So yeah, I think we're ready to rock and roll. Yeah, sorry for the delay again. It's just things that are out of my control, so we do the best that we can and we keep it moving. Let me check the chat. I see there's. Let's go like this. Yeah, that's right, brother. That's right. Pastor, professor, professor, pastor. Speaking the gospel of the ones and twos of college algebra. That's right. You get a haircut and reality changes. That's exactly what happens. I try to save stuff like that for the end. I try to like work on the inside first, and then once that's where I wanted to be, then you know, I try to shine. I try to shine from the inside out instead of outside to the end. Anyway, that's neither here nor there. Oh man, okay. You guys are too funny. Everybody's like that. Everybody in my circle's like, "What? Like, is this the same person?" I was like, "Yes." I just got my hair. It's not a big deal. It's too funny. All right. So I think we're streaming. Let me make sure it's showing properly. That looks good. Okay. So yeah, no real announcements. Let me see. This is week. Let me go back to this view real quick. Seamless. Yeah. Oh no, that's not right. Let's go back. Is this the copy? This is the right one. So I just need to change the label. Let's go like this, like this. Come on. Okay. This is college algebra. This class meets on Tuesdays and Thursdays at 2:25. This is the fall of 2020. All right. And today we're going to be looking at polynomial and rational functions. Section 2.2, polynomial functions. And I say, don't get me started. I totally will do that. That's too funny. That's so much fun. The servant on the mountain high today, brothers and brothers. We don't have any sisters. Just having some fun. Totally, I could totally do that. Past the professors on the ones and twos talking about polynomial and rational functions for me and yous. So, yeah. So today we want to go through section 2.2. Y'all got me like, I'm dying too. I'm totally dead. It's too funny. Let me see. So this is section 2.2. So let me see. We need to do about 30 slides today, give or take. Now we can totally do it. We'll see how it goes. We're just gonna kind of jump into it. Oh man. Yeah. So 2.2 polynomial functions. This topic is part of me wants to be like it's a little bit intense. Let me grab one other thing that will help with the flow. Not this one. Yeah, there it is. Adulting. Adulting is a lot of fun. Now I feel like I honestly could do the whole lecture like that. I might do that one day. Like y'all done giving me ideas because I've always been trying to think of ways of ideas of how to spice up the presentation, how to just change it up. I could totally do that because I just imagine that I'm back in church and then you know. Anyway, it's not a big deal. Okay.
What happened?
Nothing. They like it's like is that pastor professor? So because the haircut look like a pastor with the turtleneck workout shirt with the medallion. It's just like it's a professor. It's a pastor. It's too funny. Anyway, so I was like, today we're going to be doing section 2.2 polynomial functions. We're going to learn the properties of the graphs of polynomial functions. Determine the end behavior of polynomial functions. Find the zeros of a polynomial functions by factoring. Identify the relationship between degrees, real zeros, and turning points. Graph polynomial functions. You see what I'm saying? You can just play around with it.
Did you do your I have a lesson speech?
I have a lesson. I have a dream that one day all the little boys and girls will be learning about mathematics mathematics, and they will be so excited, and they will just know it, and they will be free. They will free themselves through mathematics, talking about the definition of a polynomial function of degree n is a function of this form, where n is a negative integer, and the coefficients are these are real numbers, where the leading coefficient is not zero. Just kind of playing around. Mr. Jones, let me see who we have. So, just being silly. All right, let's go like this. Cool, that's showing properly. Mr. Jones. I got a Jones. It brings the energy though. I can totally feel the vibration. Did he? I think he logged in already. Let me just make sure he is there. Cool beans. Yeah, because I did hear him get knocked out. All right, let's focus because I'm gonna have too much fun. I'm probably gonna start doing that one day sooner or later. I will do that.
Praise the grades.
Praise the grades. Let me see some way to incorporate. When we study hard and we work hard, and then we see our grades go rise high. We take that test and our grades go rise high. Just something like that. So can I get a divide by what? Something like that. You need something like this, amen, but you need the math equivalent of amen or hallelujah or something like that. It's too funny. That is too funny. I'm gonna totally do that one day because it's so natural. It's so right there. All right. So now we're talking about polynomial functions, right? So again, a polynomial function. Oh my goodness, guys keep jumping in. Oh, he's already in there. Okay. I think he just is having connection issues. So a polynomial function of degree n takes on this form. Man, I totally want to go back to that now because it's so different. So now another way to articulate polynomial functions, if you take a monomial, right? A monomial is a one-term polynomial where the coefficient is just a real number times a variable x, and x is raised to the power of some non-negative integer. So that's a monomial. Some real number coefficient times a variable x to a non-negative integer, raised to the power of a non-negative integer. Can I get a calculation now? Yo, if you write that up, you can write something up. We'll do it right. Like just write up a script, something like little catchphrases and stuff. I'll totally do it. Can I get a calculation?
So I'm actually very funny, so I can just come up with jokes off the top of my head all day.
Yeah. We got some talent in the house. I think we got some real talent. Like that's like if you can do stuff like that, that's what it's about. Because this stuff that we're doing with math is just a formality, but if you have a talent to something that people can't do like that, you want to do that as much as possible, as often as possible, because that's what's going to set you apart. That's what's going to really propel you into your greatness. Like when you can do things that other people can't do, that's what it's about. So then,
I just use it to mainly bring people's spirits up.
Exactly, and that's what the world needs. We definitely need that. A polynomial function is going to be nothing but a finite sum of monomials, right? So again, we describe what a monomial is, and then if we do a finite sum of monomials, that's what a polynomial is. So then the term, as we kind of look at the polynomial, the term an x to the n is called the leading term. This is going to naturally come out when we start working polynomials. This topic, just brace yourself. It's a little bit intense for college algebra students. You just kind of have to work and just keep trying, and it'll eventually click over. The number an is called the leading coefficient, and a sub 0 is the constant term. Let me see. If we have a function like f of x equal to some number, as long as it's not 0, that's going to be a polynomial of degree 0, right? So if we had like f of x equals 2, or f of x equals negative 7.37, whatever, these are all a constant function with we could say is a degree 0. But the caveat is that f of x equal to 0, we say that has no degree because that's not unique, right? If we say f of x equal to 0, that's the same as 0 times x squared, which is the same as 0 times x to the negative 3. It's like, because you can't specify the degree, we say f of x equal to 0 has no degree, okay? It's a little bit, kind of like this, but again, I feel like it'll come out naturally once we start working some examples. Okay, and these are just the names. So again, a polynomial of degree 3 is a cubic, 4 is a quartic, and 5 is a quintic polynomial. And then Halloween is coming up around the corner too. That's really bad. This expression, this is a general form of a polynomial. You'll see what it looks like once, and you probably have already seen it. But this is a general form of a polynomial. And then if we say f of x equal to that expression, that's called a polynomial function. And then if we say that expression equal to 0, that's going to be a polynomial equation. Okay. So the domain of a polynomial function is going to be all reals. And these are just okay. These are some properties of polynomials. I think you guys can see my cursor. So can you see my cursor? I'm not sure. Can you see like the arrow dancing around on the screen? No. Okay, I don't think so. It's okay. Oh, you can see it. Okay. So it says the graph of a polynomial function is a continuous curve. So this is one property of the graph of a polynomial. We can start at any point on the graph, and we can we can trace the graph and get to any other point on the graph without picking up our pencil. So the graph of a polynomial function. Oh man, I totally should be doing this passing thing because I can totally talk in that rhythm. Like, like now, if you see any holes or gaps, beware the holes or gaps. And it's no longer a polynomial function. Now it's starting to get this whole Macho Man Randy Savage as a pastor. Imagine Macho Man Randy Savage as a pastor, because that's what it was. That's the vibe. That's what it was taking on. Anyway, that's what it was totally sounding like. Oh yeah, and we're gonna, that whole thing, but that whole energy. But yeah, so the property of a polynomial function, the graph, one property is that it's a continuous curve. Again, there are no holes or gaps or breaks. So if our graph has a hole or a gap or a break or anything like this, it's not the graph of a polynomial, right? Another property of the graph of polynomials is that it's a smooth curve. So not only is it continuous, the graph of a polynomial is continuous, but it's also smooth. Okay. So what that means is that if we have a sharp corner like here, like these three examples, if we have any sharp corners, then it can't be the graph of a polynomial, right? Can't be the graph of a polynomial. But so two main properties of the graph of a polynomial, they have a continuous unbroken curve, continuous smooth unbroken curves, right? That's the main properties of the graphs of polynomials. So let me see. Do I need to? Yeah, I need to add a page. That's too funny. Man, that's too funny. Y'all got me like I'm laughing the whole time in my mind. I'm just doing the best I can to be professional and do what I know I need to do. But that's too funny. But like that's how you know you're onto something. Like I study like comedy, even though I'm not that funny. But like they had Tiffany Haddish on the Daily Show one day. Oh no, I need you here. They had Tiffany Haddish on the Daily Show one day, and he asked her. She was talking about her experience with like a Red Fox, and so Red Fox was like, "Well, what are you?" He asked her, "What are you doing?" She was like, "I'm doing comedy." He was like, "No, you're not. You're giving me a headache." He was like, "Do you know why people come to a stand-up comedy show?" And she was like, "To have a good time." And Red Fox was like, "That's right. It's either Red Fox or Red Fox. I think it's Red Fox. The fox. I can't think of his name, but he was like, yeah, people come to stand-up comedy to have a good time. He was like, do you know how to tell if your audiences have a good time? And she said no. He said, if you want your audience to have a good time, you got to have a good time. I was like, oh, and so when I thought about that for my presentations, I was like, that's true. Cause like even if they're not getting it or whatever, as long as I'm having a good time, they're either gonna laugh at you or laugh with you. But we'll all have a good time. The energy is infectious. It's very infectious. So that resonated. That just was like plastered in my mind when they made that statement. So it's like now, whenever I present, that's where my mind goes. So it's like I try to even if the topic is it is what it is. I try to have a good time on some level so that try to help people to just have fun with it. Do what you got to do, but still have fun with it. So in this example, we're asked to state which functions are polynomial functions. Oh, we didn't need space. That's why I didn't have it. Talk about it. That's okay. We're here now. Actually, you know what? I'm going to get rid of this because I don't need it. Let's delete it. And let's switch it back. Okay. No, here we go. So, which functions are polynomial functions? For each polynomial function, find the degree, the leading term, and the leading coefficient. So, this first one, notice that all the coefficients are real numbers, right? The first one is like 5. We have -2 and 7. Those are real numbers. And then each variable is raised to a non-negative integer exponent, right? This one is actually x to the power of 0, right? So it's all raised to the power of a non-negative integer exponent. So this one is a polynomial function. So the degree of this polynomial is going to be 4. I'm not going to write it. The degree is going to be 4. The leading term is this guy. It's going to be the term with the highest exponent. And the leading coefficient is going to be this guy. So it's the number in front. It's the coefficient of the leading term, right? Okay, so we're going to do more examples where we do that. So then in the second one, now if we ignored this thing over here, if we ignored this, then I would say, yeah, it's a polynomial, right? But one property of polynomials is that the domain is all reals. This domain has been restricted to from 1 to 5. So this one is not going to be a polynomial because of that restriction on the domain. Okay, and we have all that typed up here. Okay, we have all that typed up here. And also, I just encourage anybody that comes across my path, as soon as possible along your experience as a spiritual being having a human experience, as soon as you can, identify what you love to do. It doesn't matter what it is, as long as you're not hurting anybody, you're not hurting yourself. Once you're clear about what you love to do, I recommend you do that as much as possible. Like as long as it's constructive, you're not like hurting yourself, you're not hurting anybody else. Do it, because eventually what's going to happen is you're going to find a way to make a living, because you're going to find a way to make a living doing what you love to do. You never work a day in your life. And like, I mean, that's the God on the street. Like that's what I've been experiencing. I mean, I don't get paid a lot, but I don't be stressed out like everybody else be. Like I have plenty of people that make way more money, but they're not free. Like they can't do what they want when they want. They're bound by whatever it is that they're doing. So hopefully, they love what they're doing. But if you don't love what you're doing, what are you doing with your life? You know what I mean? Anyway, so a function of this form is called a power function of degree n, where a is going to be a non-zero real number, n is a positive integer. Power function, right? This is also a monomial, right? This is what I meant by a monomial. The leading coefficient is a real number, and x to the power of a non-negative integer. So then a polynomial is just a finite sum of these guys. So then with the power function, let's see how it goes. So say we consider the power function. If the exponent is even, right? If we multiply if we multiply a negative number an even number of times, like if we square a negative or say a negative to the power of 4 or whatever, it's going to become positive. That's what this is saying here, right? So again, with an even exponent, if we did f of negative x, ultimately we're going to finish with f of x, right? So when we start with f of negative x and we finish back with the original, that's the definition of a function being even. And so when a function is even, then we say it's symmetrical with respect to the y-axis. That means we can fold it. That means we can fold it. See, it's a little bit of Macho Man Randy Savage with the pastor, but it's kind of weird. But yeah, it'll be symmetric. We can fold it on the y-axis, and the two halves are going to match up. Again, this is the definition of a function being even. We start with f of negative x, we finish with f of x, right? That means we can fold it along the y-axis. Okay. So then let's consider this next one. So we still have a power function, but now the power on the variable, instead of being even in this case, is odd, right? So now if we take a negative number and multiply itself an odd number of times, like -1, like to the power of 3, the result is essentially going to be negative, right? So with this, in this case, if we did f of negative x, we're going to finish with negative f of x, negative of the original. So that's the definition of a function being odd. We start with f of negative x, we finish with negative f of x. That means the function is odd. Odd is the same as symmetry with respect to the origin symmetry. Origin symmetry means, say we have a graph, it's going to pass through the origin. If we put our thumb on the origin, we cut it along the x-axis. And if our thumb is on the origin, we take the top half and rotate it 180 degrees. The top half is going to match the bottom half. Another way to articulate origin symmetry, whenever we have x comma y, we also have negative x comma negative y. So now, I want to say that these presentations should be streaming. Let me make sure the stream looks like it's good. I'm not going to worry about that. So I'm gonna go at my natural rhythm. It's going to be a little bit accelerated, but just be aware you can always go back, pause, slow down, rewind, do whatever you need to do, and it's totally okay. But I want to kind of keep the pace. And we're almost there. I think we can actually make our target today. Okay. So again, another way to articulate origin symmetry, whenever we have x comma y, we also have negative x comma negative y. And basically all the points are symmetrical with regards to the origin, right? So that's kind of how that goes. You can't. It's kind of like rotational symmetry. We'll see it in action. So if we consider the power function, so let's see. Let's do like this. And this is the case where the leading coefficient is positive, and I also want to mention that our n should be even. Our n is even in this example. Okay. Let's copy. So if we're considering still like the power function or x squared, the leading with a positive leading coefficient means that it goes up to the right. Because n is even, that means the other side does the exact same thing. Let's run that back. A positive leading coefficient means the graph goes up to the right in the long run. Because the degree of the polynomial is even, the other side does the exact same thing. It goes up as well, right? So even is like exact same, right? So if, and let's kind of look at another one. So in this case, again, we're still considering n is even. Now we have a negative leading coefficient and n is even. So because the leading coefficient is negative, that means it goes down to the right. Because n is even, the other side does the exact same. Let's run that back. A negative leading coefficient means it goes down to the right. It falls to the right. Because n is even, the other side does the exact same. So for this discussion, even degree means exact same. Even means exact same. So if even means exact same, what do you think odd means? If even means it does the exact same, odd might mean what? If you just think about your intuition. If even means exact same, odd might mean the opposite, right? So let's see how that might come about. So in this case, this is where n is odd. N is odd. We want to get a copy of this now. Okay, so now in this case, the leading coefficient is positive, but now the exponent is odd. So with a positive leading coefficient, that means it goes up to the right. But because the degree is odd, that means the other side is going to do the opposite. So now it's going to go down to the left. Let's run that back. And again, this will come out. You'll be able to see this. Now, this is where a graphing calculator will come in handy. If you don't have a graphing calculator, you can use. I'm watching the time, by the way. I see the time. We're going to have to maximize time today. Another good site is, let me put this here. A good site for like free graphing is GeoGebra. GeoGebra.com. So that's a good site to just use and have on the ready. That's for free graphs, graphing images for free. GeoGebra. Okay, something like that. Boom. Okay, so just check it out. So again, the leading coefficient is positive. That means it goes up to the right. Because the degree of the polynomial is odd, that means the other side does the opposite. So odd is opposite. So even means exact, and Desmos, that's the other one. I always forget the name of it, and I stopped even bringing it up. But that's exactly the one I wanted to say. Desmos is good. Desmos is another good one. They're essentially the same. It's just two versions of the same thing. I was first introduced for GeoGebra, but definitely a lot of students use Desmos as well. Okay, let's go on to the next one. Is that it? No, there's one more. And let's paste. Okay. So now notice here the leading coefficient is negative, it falls to the right. The degree of the polynomial is odd, that means the other side does the opposite. Okay, hopefully you're able to catch those drifts. Leading coefficient tells us about the right-hand side. The degree of the polynomial tells us what the other side is doing. Either it's the exact same or it's the opposite. Okay, so I want to keep you right at 10 minutes. If you have questions, use the chat. Let me just kind of keep the flow. I need to do about 10 more slides. Okay. So let P be this polynomial of degree 3. We want to show that P is approximately the same as 2x cubed when absolute value of x is very large, right? Okay, let's do this color. So let's start with like P of x, right? Which is equal to 2x cubed plus 5x squared minus 7x plus 11. So we want to show that this polynomial is approximately the same as 2x cubed when absolute value of x is very large. So let's factor out x cubed from all the terms, right? So we're going to factor out x cubed, right? So from the first term, if we divide by x cubed, we're left with 2. The second term, if we divide by x cubed, we're going to be left with 5 over x. The next one is going to be 7 over x squared, and the final one is going to be 11 over x cubed, right? All we did was we factored out, because if we multiply it back, if we distribute it back, this times this, we get the above. This times this, we get the above. If we multiply back, we'll get the above line, right? Man, I'm liking these updates that this app has done. It's so smooth. Like, I can do what I need to do. I'm like, oh, I'm geeking. Like, like technology, it's like scary and exciting at the same time. Um, don't get me started. I'm trying to let me focus because we don't have a lot of time. So now, if we let me see, let the absolute value of x go to infinity. Let it get very, very big, right? So as the absolute value of as x gets very, very large, as x goes off to infinity, this thing here, essentially, this term goes to zero, this term goes to zero, this term goes to zero. Okay? So as absolute value of x goes off to infinity, those terms essentially go to zero, and then now this is going to be approximately equal to 2x to the third, right? So we started with p of x, we showed how it was approximately equal to 2x to the third, and we know how the graph of 2x to the third behaves. If we were to look at the graph of this guy, because the leading coefficient is positive, in the long run, it's going to rise to the right. Because the degree of this power function is odd, that means the other side is going to do the opposite. So it's going to fall to the left, right? The cubic function is kind of like an S shape, right? Positive leading coefficient is going to go up to the right. Odd degree is going to fall. The other side is going to do the opposite, right? So because this polynomial is approximately equal to this power function, then we can just use the leading term to get a sense of how this polynomial behaves in the long run. Hold tight for like 5 minutes. Let me kind of power through it. And this is just reiterating what we just did. And the leading term test is basically saying what I just said, right? So given a polynomial, we can focus on the leading term tells us the long-term behavior of the polynomial, right? Based that same 4 tests that we just did a moment ago, right? So again, in this case, I think our n is even, right? Notice a positive leading coefficient, it rises to the right. An even degree polynomial, the other side does the exact same. If the leading coefficient is negative, it should fall to the right. Let's see. Again, n is even. So notice, a negative leading coefficient, it falls to the right. Again, if n is even, the other side does the exact same. It's going to fall as well. Okay? And then let's just do this. Actually, no, we're here. And here n is odd. Okay? Again, a positive leading coefficient, it rises to the right. If n is odd, the other side does the opposite. It's going to fall. So it's going to do the opposite. Okay? If the leading coefficient is negative, a negative leading coefficient, it falls to the right. And again, let me just go ahead and make my copy. Again, n is odd. So again, a negative leading coefficient, it falls to the right. If n is odd, the other side does the opposite. It's going to rise. All right? Like dust, I rise, we rise. I like to say we instead of I, because it's not about me anymore. You know, it's not about the individual. It's about the collective. You know what I mean? Anyway, a couple of more slides, and we're on the mark. So use a leading term test to determine the end behavior of the graph, right? So if we look at this leading term, the leading coefficient is going to be -2. So that means the graph is going to fall to the right. So to the right, it's going to go down. Because the degree of the polynomial is odd, right? The highest exponent is odd. So the degree is 3, which is odd. That means the other side is going to do the opposite. So that means it's going to rise to the left. Right? It's going to go up to the left. All right, so it's going to fall to the right and rise to the left, something like that. All right? It's going to do the opposite. Okay? So if we were to look at the graph, let's see, right here. I'm not sure if this is a typo or not. I feel like those should be arrows, but But right here, it's going to rise to the left and fall to the right. Rise to the left, fall to the right. Okay? I'm watching the clock, and we're pretty much on the mark. This is just the result there. Let me see how many more. Can I finish this in the time? I think I can. Okay, this is going to be the last example. So if f is a polynomial function and c is a real number, then the following statements are equivalent. C is a 0, c is a solution or root, and c is an x-intercept. So whenever you hear us say find the zeros of the function, or what are the solutions of the function, or what are the roots of the function, or what are the x-intercepts. All these things circled right now, they all mean the same thing, and we use these terms interchangeably. So if you ever hear me say solution, I mean just find the x-intercept. If you ever hear me say root, I mean just find the zero. These all mean the same thing, and we use all these terms interchangeably for these topics. Okay, so let's see how we can do. This is going to be the last example. Find all the zeros of each polynomial function. Dang, what do we have at our disposal? Okay, let's do this. Let me see. Do I have this? Okay. I'm going to give it a go. I'm watching the clock. I'm not going to go past the 15 mark. Okay, let's add a page. I'm not sure what we have at our disposal. Like I'm like, okay, what have we and have we not talked about? Let me go like this. Let me get rid of this. Let me get a copy here. This one, this one, this one. Let's go like this. Come on. You go here. Awesome sauce. Come on. Awesome. All right, we got like 5 minutes. Let's see what we can do in 5 minutes. Paper like this. And view like this. Okay, we're ready to rock and roll. And let's just, for the good measure, let's go ahead and add another page. I'm watching the clock. I'm gonna honor the time. So find the zeros. Okay, I'm just gonna kind of do this one. Let's just do this. So then for part A, we have f of x equals x to the 4 minus 2x cubed minus 3x squared, right? So we want to find the zeros. Okay, so we want to solve. So what I'm going to do is set it equal to 0 and solve. So first thing, we can factor out, there's a greatest common factor. All of these terms have at least x squared, right? If we factor out x squared, we're going to be left with x squared minus 2x minus 3. And again, if I'm finding the zeros, I'm going to go ahead and set it equal to 0. Okay? So just kind of bear with me. Okay. So we factored one part. Let's see, can we factor again? So I'm going to bring down my equal sign. Now, can we factor this trinomial? The x squared just comes down. I'm going to put my x and my x. So let's see, we're looking for two numbers that multiply to give us -3 and add to give us -2. So because the second sign is negative, my signs have to be opposite. This says my largest number is going to be negative, so I'm thinking, let's just do this. This is fine. -3 and a +1. Let me check real quick. This times this is -3, right? This plus this is 2. So I think we're okay. -2. Okay. It's still equal to 0. I'm watching the clock. So now we're ready to imply. So first thing we did was we factored. I'll just make a note here. We factored. Okay. Actually, yeah. Okay. Let's see. We factored the greatest common factor. Then we just factored again. This is factoring. We factored the trinomial. Okay. So now the next thing we want to apply is called the zero factor property. We want to invoke what's called the zero factor property. Okay. Zero factor property says when things multiply to give us 0, basically set each of those factors equal to 0 and solve, right? So we have 3 things that multiply to give us 0. So either we just say x squared equals 0, we also do x plus 1 equals 0, we also do x minus 3. X minus 3 equals 0. Yeah, right? So when we have things that multiply to give us 0, we just set each thing to 0 and solve. From the first one, the solution there, if we take the square root on both sides, x equals 0. From the second one, if we subtract 1, x equals, what is that, -1. The third one, if we add 3, x equals 3. So these are the zeros that we found. We got x equals -1, 0, and 3. But we're not done at this point. I'm watching the clock. I got a solid 2 minutes. I'm going to take advantage of these 2 minutes. We need to check that in the context of the original. Let me go ahead and solve the second one, and I'll check it momentarily. I just want to get the meat and potatoes out. G of x equals x cubed minus 2x squared plus x minus 2. Let me take this thing, nope, like this, like this, like this, like this. Let's cut. Looks good. We're going to paste right here, and let's go ahead and do this one. Right? Let's just do the same thing. Just for the sake of time, I'm not checking the earlier one. I'm going to check it momentarily. So now let's do the same thing. We got this x cubed minus 2x squared plus x minus 2. We're going to set that equal to 0. There's no GCF here, so I'm going to invoke this technique called factor by grouping. I have 4 more terms. First, I'm going to group the first 2 terms and see what can we factor out of those. Okay. So now if we look at the first 2, again, the technique I don't have time to write it, but we're using factor by grouping. Now the first 2 we can factor out. It looks like an x squared. We're going to be left with x minus 2. Let's do it like this. Use this color, right? So the hint is we're anticipating another x minus 2 on the right hand side. The 2 on the right, we would factor out a 1. They don't really have anything in common, but we can still identify the x minus 2, right? So now they both have the blue thing that we can factor out. It's called the common binomial factor. So if we factor out the x minus 2, looks like we're going to be left with, it looks like x squared plus 1. Okay. So now we're back to the zero factor property. The x squared plus 1, that's not going to have any real zeros, right? If we set it to 0 and solve, we're going to get some imaginary results. But the other one, this x minus 2, if we set x minus 2 equal to 0, then we get x equals 2. All right. The other one, we don't get a real solution, so the only 0 there is this one. Let me just do a quick check. I see the time. I'm about to let you guys go. Style like this. I'm going to do a quick check. And so to check, what we're going to do is the following. I'm going to do this as fast as I can. We're going to go here. I want to open up my Trusty Dusty Rusty. Hopefully you're working. You are looking healthy. Awesome sauce. Come on. Okay, let's show you. Okay, so let's use the calculator real quick, and then I'll let you go. So I'm going to go to y equals. The first one was x to the power of 4 minus 2x to the power of 3 minus 3x squared. That's the first one. I'm going to go ahead and type in the second one. X to the power of 3 minus 2x squared plus x minus 2. I typed in both, right? Hopefully I didn't make any mistakes. I see the time. Let's quit. I'm going to call those functions as fast as I can. Here's the first one. So now the results we got there, we got when x was -1, we should get 0. Awesome sauce. When x is, the next one was what? 0, we should get 0. Awesome sauce. And the final one is when x was 3. Awesome sauce. Those work. And then let's call the second one. I'm going to go back to variables, y variables. Now instead of number 1, I'm going to press number 2. That's the second one I typed in. The only answer we got there was when x was 2. And we got our 0. Wham, bam. Thank you, ma'am. All right, guys, you're awesome. Thank you for being such awesome people. I'll see you guys on Thursday. Deuces up, A-Town down. Pastor Professor. Professor Pastor is out. Take care.
Thank you, Professor.
My pleasure. Yep. Right. Let me share a copy. Let's go like this. The paper. Let's put this like this. We gotta do it like this. That's fine. Share. Send it here. Here. Let's go here. This one. Right there. Oh, that's good. So that 9, 8 is like, yeah, that's fine. It's in the box. Okay. I need to make a shortcut for this, but that's okay.